Good afternoon. I am Bhuvneshwari, Assistant Professor, Department of Mathematics, AJK College of Arts and Science. Previous class we have seen Unit 1 in Discrete Mathematics. The topics are basic logical operators, truth table problems, arguments, etc. Today we are going to see Unit 2 in Discrete Mathematics. The topic is methods of proving theorem. First one, direct proof. Second one, proof by contradiction. Third, proof by contraposition. Fourth, proof by mathematical induction. Direct proof, indirect proof, proof by contraposition. Problems. Prove that if n is an integer and 3n plus 2 is odd, then n is odd. Proof. We have to take 3n plus 2 is odd. Assume n is even. If n is even, then we can write n as n equal to 2k. Substitute n in 3n plus 2. 3 of 2k plus 2 equal to 6k plus 2. Then 6k is always even and 2 is even. So 3n plus 2 is even. So, but we have 3n plus 2 is odd. So our assumption is wrong. Therefore, n is even is incorrect. Hence n is even is false. So n must be odd. Next, translate each of these statements into logical expression using predicates, quantifiers and logical connectives. First one, no one is perfect. Not everyone is perfect. All your friends are perfect. At least one of your friends is perfect. No one is perfect implies not of one is perfect. That is negation of there exists x p of x equal to for all x negation p of x implies everyone is imperfect. Not everyone is perfect implies not everyone is perfect. That is negation of for all x p of x equal to there exists x negation p of x equal to at least one is imperfect. All your friends are perfect. That is, if there is a person who is your friend, then he is perfect. Equal to for all x of f of x implies p of x. At least one of your friend is perfect. Equal to there is a person who is your friend who is perfect. There exists x, f of x and p of x. Next topic is mathematical induction. Definition. Mathematical induction is a mathematical technique which is used to prove a statement, a formula or a theorem is true for every natural number. There are 3 steps in mathematical induction. Step 1. Check whether the given statement is true for n equal to 1. That is, p of 1 is true. Step 2. Assume that the given statement p of n is also true for n equal to k, where k is any positive integer. That is, consider p of k is true. Step 3. Prove that the result is true for p of k is true for any positive integer k. That is, prove that p of k plus 1 is true for all positive integer. Problem. 2 plus 4 plus 6 equal plus etc. plus 2n equal to n plus 1 into n is true for all positive integer. Using mathematical induction, we have to prove this the given statement is true for all positive integer. Then let n equal to 1. LHS equal to 2 into 1. RHS equal to 1 into 2. That is, LHS equal to RHS. So p of 1 is true. Now we assume that p of k is true. That is, 2 plus 4 plus 6 plus etc. plus 2k equal to k into k plus 1. Next, for p of k plus 1, LHS equal to 2 plus 4 plus 6 plus etc. plus 2k plus 2 of k plus 1. That is, implies k of k plus 1 plus 2 into k plus 1. Taking k plus 1 outside, k plus 2 you will get. K plus 1 into k plus 1 plus 1 equal to RHS of p of k plus 1. So, the given statement is true for all positive integer. Next, similarly, same type we will see the problem. Next, prove that 3 power n minus 1 is divisible by 2 is true for all positive integers. When n equal to 1, p of 1 equal to 2, which is divisible by 2. So, p of 1 is true. Now, we assume that p of k is true or 3 power k plus 3 power k minus 1 is divisible by 2. When p of k plus 1, we get 3 power k plus 1 minus 1 equal to 3k into 3 minus 1. Then taking 3 outside, 3k minus 1 plus 2. So 3 power k minus 1 plus 2 is also divisible by 2. Therefore, the given statement is true for all positive integer. Next topic is relations. A relation is in mathematics defines the relationship between two different sets of information. Also, a relation is defined as a set of ordered pairs. The relation is the relationship between two or more set of values. Suppose x and y are two sets, and set x has a relation with set y. Then the value of set x are called domain, whereas this value of set y are called range. Example. In the morning assembly at school, students are supposed to stand in a queue in ascending order of the height of all the students. This defines an order relation between the students and their heights. Important properties of relations. First point, identity relation. Every element in domain is related to the same element in codomain. It's an identity relation. Next, empty relation or void relation. There will be no relation between the elements of the set. Is an empty relation. It is denoted by pi. Next, reflexive relation. Every element gets mapped to itself in a reflexive relation. Relation R in a set A is reflexive if A, A belongs to R. For all A belongs to A. Irreflexive relation. If any set is not related to itself, then it is an irreflexive relation. Next topic, inverse relation. When a set has elements which are inverse pair of another set, then the relation is an inverse relation. For example, if R equal to P, Q, R, S, then R inverse equal to Q, P, S, R. Inverse relation is denoted by R inverse equal to B, A, where A, B belongs to R. Symmetric relation. A relation R is a symmetric relation if B, A belongs to R is true when A, B belongs to R. For example, R equal to 3, 4, 4, 3 for a set A, 3, 4. Symmetric relation is denoted by A or B implies B or A for all A, B belongs to A. Next, transitive relation. A relation is transitive if A, B belongs to R, B, C belongs to R, then A, C belongs to R. It is denoted by A or B and B or C implies A or C for all A, B, C belongs to A. Equivalence relation. A relation is called equivalence relation if it is reflexive, symmetric and transitive at the same time. Universal relation. A relation is said to be universal relation if each element of A is related to every element of A. It is the opposite of the empty or void relation. Examples of relation in real life. Relation and functions in real life gives the link between any two entities. In our day life, we come across many patterns and links that characterize relations such as relationship between father and son, brother and sister, etc. We will see the examples in family. Names of relation in a family: father, mother, son, daughter, husband, wife, brother, sister, and goes on. And we will see the example diagram. Here in this example, grandparents, grandmother, son and father, mother, sister-in-law, brother-in-law, husband, wife, uncle and aunt, son, daughter, father and mother. These are the relationship between the persons in our family. Composition of relation. Let R be a relation between set A and set B, and S be the relationship between set B and C. The relation consists of the order pair A, C, where A belongs to A and C belongs to C, and for which there is A belongs to A, B belongs to B, such that A, B belongs to R and B, C belongs to S is known as composition of R and S. Then the equivalence relation is denoted by the symbol. Okay. Then closure of relation. Closure of relation or with respect to a property P is the relation obtained by adding the minimum number of ordered pairs to R to obtain property P. Next, transitive closure. The transitive closure or star of a relation R is the smallest transitive relation containing R. The transitive closure or of a relation R is the smallest transitive relation containing R. Suppose A is a finite set with n elements. Example, let A equal to 4, 6, 8, 10 and R equal to 4, 4, 4, 10, 6, 6, 6, 8, 8, 10 is a relation on set A. Next topic is the transitive closure. The transitive closure or star of a relation R is the smallest transitive relation containing R. The transitive closure of a relation R is the smallest transitive relation containing R. Suppose A is a finite set with n elements. Let A equal to 4, 6, 8, 10 and R equal to 4, 4, 4, 10, 6, 6, 6, 8, 8, 10 is a relation on set A. Next, another example is from this we can find the transitive closure of R. R square means R composition R. Like that process goes on. Then we can find the solution for the above example. Next topic is partial order relation. A partial order relation is any relation that is reflexive, antisymmetric and transitive. A total order relation is a partial order in which every element of the set is comparable with every other element of the set. All total order relation or partial order relation, but the converse is not always true. Next topic is partition of set. The union of the subset must equal the entire original set. Next one, partition on set A. It is defined to be a set of non-empty subsets AI which are pairwise disjoints are there as there is no intersection and whose union yields to the original set A. This means that two conditions have to be satisfied. That is, first condition is AI intersection AJ equal to null set. Then union AI equal to A. Next, covering of a set. It is defined as a set of non-empty subset AI whose union leads to the original set A and which are not be pairwise disjoint. Here there are two conditions that are to be satisfied. That is, first condition, union AI equal to A and AI intersection AJ not equal to null set. A partitioning is a collection of subsets which is simultaneously both a covering and a packing. Next topic is definition of function. A function is a group of statements that together perform a task. It can be mathematically transcribed as f equal to a comma b for all a belongs to capital A, comma b belongs to capital B. A relation is described as a function if every element of the set A has only one image in the set B. A function is a relation from this non-empty set A to the set B, and two distinct order pairs in F can have the same first element. A domain is the set of values that can be plugged in as input in the function while it can be defined. A codomain is the set of values that have the potential to come out as output of a function. The range is all the values that can be obtained as the output of the function involved. Next example, consider the diagram. Domain, codomain, range. In domain A, B, C, D. In codomain P, Q, R, S. There is a function from A to B. All elements are mapped to the elements in the codomain. One S is left. That is no problem. But this is a function. Next, types of function. One-to-one function, many-to-one function, one-to-many function, many-to-many function. One-to-one function, also known as injective function. A one-to-one function is defined by F from A to B such that every element of set A is connected to a distinct element in set B. Here, for the given function, every element of one domain has the distinct image or codomain element. Many to one function. It can be defined by the function f from A to B such that more than one element of set A is connected to the same element in set B. In this case, more than one element has the same codomain or image. Onto function. In the case of onto function, every element in the codomain is related to the domain element for a function defined by f from A to B such that every element in set B must have pre-image in the set A. Into function. Here, there will be certain elements in the codomain that would not have any pre-image. The elements in set B or in excess are not connected to any one of the elements in set A. This is the onto function. This is exactly opposite to the onto function. Next, constant function. It is a kind of function which gives the same value of output for any input. It is expressed as f of x equal to c, where c is constant. Below that, the diagrams are given. Next, the constant function. The polynomial function of degree 0. In linear function, the polynomial function of degree 1. Quadratic function, the polynomial function of degree 2. Cubic function, the polynomial function of degree 3. A function can be understood by thinking of it as the machine that takes as input of a certain type and transform them into a particular output. A constant function is a function having the same range for different values of the domain. Identity function. The function that associates each real number to itself is called the identity function. It is denoted by I. Inverse function. The inverse function of a function is a function that undoes the operation of f. The inverse of f exists if only if f is bijective, and if it is exists, and then it is denoted by f inverse. F is a mapping from A to B. F inverse is a mapping from B to A. Next, composition of function. The composition of a function is an operation where two functions, say f and g, generate a new function, say h, in such a way that h of x equal to g of f of x. It means here function g is applied to a function of x. So basically, a function is applied to the result of another function. In mathematics, function composition is an operation that takes two functions f and g and produce a function h equal to g composition f, such that h of x equal to g of f of x. A composition function is created when one function is substituted into another function. Now you see the problem, mathematical induction. By using mathematical induction, prove the given statement is true for all positive integers. 2 plus k plus 2 plus 6 plus 10 plus etc. 4 and minus 2 equal to 2n square. We have to prove this statement by using mathematical induction for all positive integer n. Next, we have to consider the given statement as p of n. Next, first step, there are 3 steps to solve the problem. First step is let n equal to 1. Let n equal to 1. LHS equal to 4 into 1 minus 2 equal to 2. RHS 2 into 1. 1 square, that is 2. Therefore, P of 1 is true. Next step, assume that P of k is true. Then we have to put 2 plus 6 plus 10 plus up to etc. plus 4k minus 3. Instead of n, you have to put k. Then equal to 2k square. Okay, we have to assume that. Next, we have to prove that the given statement is true for P of k plus 1. Next, instead of n, we have to put k plus 1. That's all. Then 2 plus 6 plus 10 plus etc. plus 4k minus 2 plus 4 of k plus 1 minus 2. You have to put 4 of k plus 1. We have to substitute. Next, LHS equal to 2k square. Instead of this one, you have 2k square. 2k square. Next, 2 plus 4k plus 4 minus 2. Just you have to multiply 4k plus 4 minus 2. Then 4k plus 4 minus 2, 2. Then taking 2 commonly outside, 2 of k plus 1 whole square equal to RHS of p of k plus 1. That is the given statement. P of n is true for all positive integer n. Hence the proof. Hence the proof. Like using these three steps, we can find the solution for the many problems. Next, we will see about the function. Next, we will see the topic function. Consider the diagram. There is a mapping from A to B. Okay. From A to B, there is a mapping, that is 1 is mapped to A, 2 is mapped to B, 3 is mapped to C. But there is no one element is mapped to D, E. So there is no problem. But this is a function. This one is set A, this is set B, this is called domain, this is called codomain. Okay, this is a function. Next, consider this is a function. This one is a function. This is a function. Okay, consider this diagram. This is first diagram. Second diagram, A to B mapping. Okay, so this one F we can tell F of 1 comma A, 2 B, 3 C. This is a function. Okay, 1, 2, 3 are the elements in domain. A, B, C are elements in codomain. Okay, next. Consider the another diagram. 1 is mapped to B, 2 is mapped to A, 3 is mapped to D, 4 is not mapped to any element in codomain. This is not a function. This is the difference between a function and not a function. This is not a function. This is not a function. Since 4 is not mapped to any element in B. So this is not a function, element in B. So this one is not a function. Okay, this is the difference between. Next, third. 1, 2, 3, 4. A, B, C, D, W, 5, 6. 1 is mapped to B, 2 is mapped to A, 3 is mapped to D, 4 is mapped to C, 5 is mapped to D, 6 is mapped to W. Like this. 4 is mapping. Function. This is a function from A to B. 1 is mapped to B, 2 is mapped to A, 3 is mapped to D, 4 is mapped to C, 5 is mapped to D, 6 is mapped to W. So every element in codomain is mapped. So this one is onto function. This is onto function. Okay. It's onto function. Since every element in B has mapped. That is no element left in B. So this is called onto function. Next, fourth one. Here, consider this diagram. A, B. Okay. A is mapped to 3, B is mapped to 1, C is mapped to 4. But one element is left in codomain. This is called into function. This is called into function. That is the meaning. Okay. This is onto function. This is into function. Okay. And fifth example.
மேம் கொஞ்சம் உள்ள வாங்க ஸ்க்ரீன்குள்ள. இதுக்கு மேலே உள்ள போகாதீங்க. Now start with the fifth example. சொல்லிட்டு.
Next, we see the fifth example. A, B, C, D are the elements in A, X, Y, Z. Then A is mapped to X, A is also again mapped to Y, B is mapped to Z, W, E. C is mapped to W, D is mapped to E. But A is mapped to 2 elements in B. So this is not a function. This is not a function. Reason A is element A is mapped to 2 elements in B. So this one is not a elements in B. That means A has 2 images. So this is not a function. Okay. Next we go to another example. So first one is a function. This is not a function example. This is onto function. That one is into function. Then this is not a function example for not a function. Okay. Next we will see the problem. Function problem. If f of x equal to 3x plus 2 and g of x equal to x plus 5, find f of g of x. We have to find solution. f of g of x equal to f of g of x equal to f of x plus 5, like this. Okay, this is example for composition of function. If f of x equal to 3x plus 2 and g of x equal to x plus 5, find f of g of x. Next solution, f of g of x equal to f of g of x. Then g of x is given x plus 5. Okay, next f of x. F of x means 3x plus 2. So instead of x you have to write 3 into x plus 5 plus 2 equal to 3x plus 15. 3 5s are 15 plus 2 equal to 3x plus 17. Next, again we can find g of f of x like this. Okay, this one is first. Second, g of f of x equal to g of f of x equal to g of, what is f of x? 3x plus 2. It is given that. You have to substitute those things. Next, g of x equal to x plus 5. So, 3x plus 2 plus 5 equal to 3x plus 7. Okay, from this we can understand f of g of x not equal to g of f of x. Okay, that's all. Okay, thank you.